We know that sound is composed of waves, so the real fundamental building block for engineering acoustics is the wave equation. In this video, we'll derive the plane wave equation. We'll start by considering a longitudinal wave travelling in the x direction. So we'll look at this little animation here, and this shows a plane wave being generated by a diaphragm in a tube, and so the diaphragm is moving backwards and forward, and this causes the gas to move, and we see waves travelling out to the right. So the x direction is out to the right in this situation here. So we can look at various parameters associated with this wave. The first we'll consider is the displacement of the gas as the wave passes through it. So the displacement will be s, and there will be some mean displacement s naught plus some fluctuating displacement s prime. So if we look at any point in here, we can say that its displacement from the x direction is some mean value s naught, and then it's moving backwards and forwards a small amount s prime. We can also look at the speed of movement of the medium due to the wave. So again, if we focus on a point in here, we see that it's moving backwards and forwards. Its mean velocity in this case is going to be 0, so u naught would be 0, and there's a fluctuating component which will be u prime. Then we can go to the other parameters: density, some mean and fluctuation; pressure, a mean and a fluctuating quantity; and temperature, a mean and a fluctuating quantity. So let's now look at a parcel of gas around one of these dots here. So we're going to be considering a very small amount of this gas. So that's the center of this parcel of gas. This is the left-hand edge, and this is the right-hand edge. Let's say that the vertical distance here in the y direction is dy, so it's a very small amount, and the amount coming out of the page is going to be dz. In the x direction, the left-hand edge, we'll say, is at location x, and the right hand is going to be at location x plus dx. So the length of this particle in the x direction is dx. So this little parcel of gas initially has a volume which is dx times dy times dz. We can say that the center of mass of this parcel is going to be dx over 2 from the right hand edge, and similarly dx over 2 from the left hand edge. Let's now consider what happens as the wave passes through this gas and it displaces this particle of gas. And when it displaces it, it not only moves it, but it can also change its size, so it compress it or expand it. So let's say that this little parcel of gas, which was initially this dx dy dz, has now been displaced by an amount that the center of mass is displaced by an amount s, and then the left-hand edge is going to be displaced a certain amount, and the right-hand edge is going to be displaced a certain amount. Let's consider how the displacement varies in the x direction. Because this gas is being compressed, the displacement of the left-hand edge of the parcel of gas is expected to be different from that of the right-hand edge as this wave passes through it. So what we might expect is that there'd be some gradient in s with x. So there's some slope in here which is going to be ds dx. And let's say that this is the center of our parcel of gas. So this is going to be that location s at the middle, and at the left hand edge is going to be this, and the right hand edge is going to be here. So that's going to be the left hand edge dx over 2 from the center, and the right hand edge dx over 2 from the center. So if we look at the displacement of the left hand edge of this parcel of gas, then its left hand edge is going to be this displacement s minus the gradient ds dx times dx over 2. So this amount here is going to be that s minus ds dx dx over 2. So there basically we're saying that this is the displacement at the center s, there's a gradient ds dx, the amount of the distance in the x direction is dx over 2, so that must mean that s at this point is s minus that gradient times this amount here. Have a go at writing down what you think the displacement of the right hand edge of the particle will be. It's got a similar form to this, so maybe pause the video and write your expression for that. So by the same argument, we can say that the displacement of the right hand edge must be s plus the gradient times this distance here. So in here we'll have s plus, in this case, the gradient ds dx times the distance dx over 2. So that's going to be the displacement of the right hand edge of that particle. So I can move that down, so that's what that is there. Now we have a position of the left hand edge, we've got the position of the right hand edge, and that's going to be the difference between those two is going to be the amount that the particle is in the x direction as the wave is passing through it. So it's gone from dx to this amount here. So maybe have a go at writing down what you think is going to be this length here after or as this wave is passing through it. And the way I'm going to do it is I'm going to say that the distance to the right hand edge from the initial position of the left hand edge is going to be dx plus s plus ds dx dx over 2, and the displacement of the left hand edge is going to be s minus ds dx dx over 2. So we can write this as dx plus s plus ds dx times dx over 2, so that takes us from here to here, and then we subtract this s minus ds dx times dx over 2. And now we can delete these s's here, and we've got a ds dx dx over 2 minus a minus, so a plus another ds dx dx over 2. So the amount of displacement here is going to be dx plus the gradient ds dx times dx. So this gives us the amount by which the parcel of gas is compressed or expanded in the x direction, and we're saying that the dy and dz stay constant. So we can introduce a term where we can look at the amount by which the volume is decreased, and the volume decreased is going to be minus ds dx times dx dy dz. And we can introduce a term which we'll call the volumetric strain, which is the amount the volume decreases divided by the original volume, and since the original volume is dx dy dz and this quantity up here is the amount of volume decrease, then the volumetric strain is just minus ds dx. We then introduce a term we'll call the bulk modulus, which is the ratio of stress to strain. So this is like a Young's modulus in solid mechanics, and we know that the stress is going to be the pressure that's applied, and this is our strain here, minus ds dx. So the bulk modulus B is minus p prime ds dx. We can rearrange that simply to get an expression for p prime. You can easily do that, so that's just going to be minus b times ds dx. And we'll call that equation 1. So I've rewritten equation 1 at the top here. We can differentiate that with respect to the spatial coordinate x, and we can get dp dx. B is going to be a constant, so the right hand side, the derivative of that just becomes minus b d2s dx squared. And we'll call that equation 2. So we've got an expression for the gradient of the pressure fluctuation in the x direction in terms of the bulk modulus and the displacement, or the second derivative of the displacement in the x direction. Let's now consider a kinetics. So far we've just been looking at kinematics, just at displacements and things. Now let's look at forces. So let's consider the force that's acting on this little parcel of gas as the wave passes through it. So let's say that P prime, the change in pressure due to the wave passing through this parcel of gas, is the pressure at the middle of this parcel of gas. Then we've got some pressure that's going to be acting on the left-hand side, and that, in this case, we can say if we have a gradient in this P prime in the x direction, then the pressure at the left-hand edge is going to be the pressure at the center of the particle minus the gradient times the distance, which is dx over 2. And similarly, the pressure on the right-hand edge is P prime plus the gradient times dx over 2. So we can now consider the force that's acting on this parcel of gas. So we've got a pressure acting on the left-hand side, a pressure acting on the right-hand side. We're going to say there's no shear force acting along here, along that dx direction. So we've got that force is going to be that pressure times the area, and on the right-hand side we'll have pressure times area. So have a go at writing down what the force is in the x direction, noting that this left-hand edge is going to be providing a positive x direction force, the right-hand edge a negative x direction force. Now hopefully you've started writing down something like this, that on the left-hand side we've got a positive force acting in the x direction, and the magnitude is going to be this pressure times the area that it's acting over, which is dy dz. And then similarly on the right-hand side we're going to have a force acting in the negative x direction, and its magnitude is P prime plus dP prime dx times dx over 2. And that's acting on area again, dy dz. So again here we can wipe out the P primes, and we can show that that becomes just minus dP prime dx times dx dy dz, because we've got a minus dP prime dx over 2 here, and another dP prime dx over 2. So we have some force acting on this parcel of gas. Now let's look at the acceleration that's acting. So if there's a force, there'll be an acceleration. The acceleration is just going to be the second derivative of the displacement with respect to time, so that'll be our acceleration in the x direction. Then we know that the force is the mass times the acceleration. So here's our force up here. We need the mass and the acceleration. So put in those expressions for the force, think about what the mass would be and the acceleration. Pause the video and check your answer. And this is what we get. There's the force, there's the acceleration, the mass is just the density times the volume. In here we're assuming that the density doesn't change much as this wave passes through it, so that we're saying the density is about constant. So the fluctuation in density is very small compared with the mean, so that we can say that the density is just rho naught times the volume dx dy dz. So now we can get rid of the dx, dy and dz because they're on both sides, and we end up with an expression for dP prime dx in terms of rho naught and d2s dt squared. So there's our expression for that. And we'll call that equation 3. So now we have two expressions for dP prime dx. One up here from the kinematics, equation 2, and one down here from the kinetics, equation 3. So we should be able to equate the two equations, the right-hand sides, and so if we equate 2 and 3, then we end up with this equation here, that d2s dt squared, which we get from the kinetics, is equal to b over rho naught times d2s dx squared. And this is going to be our acoustic plane wave. And it's got the form of a wave equation. So the second derivative of displacement with respect to time is a constant times the second derivative of that displacement with respect to x. So there's our acoustic plane wave equation. It can also be written in this form here, where we lump this quantity b and rho naught into a constant we'll call c squared, where c squared is equal to b over rho naught. And you may see where this is heading. We're eventually going to get to this c being the speed of sound, so that this is the speed of sound squared. But we'll get to that in a moment. So this is the linear wave equation. It's linear because this coefficient c is independent of the amplitude of the wave, and this comes about because we've assumed things like the density fluctuation is small compared with the mean density. So the density is about constant in the control volume. We'll use that when we did the derivation of this equation. So it's a linear wave equation, and it's a linear hyperbolic partial differential equation. The general solution of this type of equation has this form here, and this can be shown by back substitution, that the displacement s is some function of x minus ct plus potentially some other function of x plus ct. So if we substitute that back into this wave equation, we can show that that is a solution of this. So we now have our wave equation, and we have the general solution for it. We'll look further into this in subsequent videos.